hydroxide solution. Unknown, what was unknown? We know what the solution is composed of. The solution is composed of sodium hydroxide and water. And so what was the unknown part of the sodium hydroxide solution? The composition. The composition, well, we know what the composition is. We just need to know the amounts of each component. And so what we say is it's the unknown, I guess, composition. Well, we know kind of half of that, and that is the composition is sodium hydroxide and water. What we don't know are the amounts, and the amounts can be given in different ways. How much sodium hydroxide can be given in terms of something called molarity. Molarity is the moles of sodium hydroxide per liter of sodium hydroxide solution. Or we could do percent composition. This could be percent composition by mole or by mass. Usually it could be by mass. Or whatever. In this case, we're just going to calculate the molarity. Molarity turns out to be a handy way of expressing the composition of a mixture. And so I want to talk about the calculation of the molarity here. But can somebody remind me what standardization refers to? Standardization of an unknown sodium hydroxide solution. And so what is the standardization process? The standardization process is determining the composition to a high degree of accuracy and precision. And so whenever we do a standardization, we want at least 4 sig figs. At least 4 sig figs worth of precision. If we have less than 4 sig figs, we don't really want to call it a standard. But what we need to do is we're going to standardize this using a hydrochloric acid standard. Now, a standard, that means somebody already standardized the hydrochloric acid. That is, they determined the composition of the hydrochloric acid to a high degree of accuracy and precision. Does anybody recall what the composition of the hydrochloric acid standard was? You should have written it down from last time. Do you have it written down? Yeah, right. The hydrochloric acid standard, somebody figured it out and they got it to 4 sig figs. It's 0.1096 moles of HCl, that's pure HCl, per liter of HCl solution. We could buy standards. You can make standards. That's the cheapest thing to do, and then standardize it. Just confirm their concentration, and then you can use those to standardize other things. Or you can buy standards. When you buy standards, they're kind of expensive. Like, for example, do you know that the NIST, what does NIST stand for? Yeah, National Institute of Standards and Technology. NIST, I was watching this YouTube video, and at the NIST, they have a standard peanut butter, jar peanut butter. And so what they did was they analyzed that peanut butter and then figured out all the components that were contained in that peanut butter and the amounts. Maybe they didn't get every single thing because there could be like trace quantities of certain things that are hard to detect, but you know, they did it. And after going through all that work, that's quite expensive because there are lots of components. It's kind of a complicated mixture. There are lots of components in there. And do you know how much that jar of peanut butter costs? Well, at the time of the video, it's $36,000. $36,000 for a jar of peanut butter. I guess it makes sense for the amount of work that went into it. A tremendous amount of work went into standardizing the peanut butter, that is, figuring out its composition, you know, to a high degree of accuracy and precision. But they're saying that jar of peanut butter has been sitting on the shelf for 20 years, so it's not a hot selling item. And you know, its composition is going to change because, you know, if the jar of peanut butter has been sitting there for 20 years, it's going to undergo like oxidation, and you know, some of the fats might become rancid. You know, some of the fats get converted into carboxylic acids, and carboxylic acids have a rancid smell to them. But anyway, this is the NIST. They have a huge budget, like billions and billions of dollars. Actually, I'm not sure how many billions. Maybe it's not so huge, you know, $1 billion. But going back to this, compared to ours, so we're going to standardize our unknown sodium hydroxide solution using an HCl standard solution. The standard solution, you have to have this written down. It's 0.1096. Did anybody else write it down? No? So it's a good thing because I didn't either. So I'm glad Kiana wrote it down. Otherwise, nobody would have it. Another thing you have to write down is the unknown number. If you don't write down because we're going to do an unknown today, which is an unknown vinegar solution. You know, you know what vinegar is made out of? Vinegar is made out of acetic acid and water. And vinegar, when you buy household vinegar, it's about 5% by mass, acetic acid. But, you know, 5% is only 1 sig fig. And so what we want to do is we want to figure out what is it to as high of a degree of accuracy and precision as we can. What is the composition of the vinegar? And of course, it's going to depend on the manufacturer and other factors, you know. But anyway, let's get back to this. So the calculation for part one is we want to figure out the molarity, that is the composition of our sodium hydroxide solution. Let's see, is this working? Okay. And so I'm going to do molarity of sodium hydroxide. Molarity has the symbol capital M. And I don't know what the molarity is, so that's what we're solving for, an unknown molarity. And that means I need to know how many moles of pure sodium hydroxide I have in every liter of sodium hydroxide solution. And so we're going to use dimensional analysis and stoichiometry to figure this out, because I know the reaction between HCl and sodium hydroxide. HCl reacts with sodium hydroxide in a 1-to-1 mole ratio, and it's going to form sodium chloride and water, salt and water. And so when we do the titration, we're reacting with the HCl standard. And so all we need here is to get the volume of the HCl standard solution that we use. And so the volume of the HCl solution. And we get this off the burette. You know, this is V final minus V initial. And so we get the volume of the HCl solution in milliliters. This would be the final volume after all the back and forth, minus the initial volume. And then we're going to convert that into liters of HCl solution. And then once we have liters of HCl solution, then we're going to use the molarity as a conversion factor. That is, we're going to go to moles of pure HCl, not the mixture, but the pure. And we know the composition of the mixture. The composition of the mixture is 0.1096 moles of pure HCl for every liter of this mixture. So I'm careful in my labeling. You know, this is moles of pure HCl. However, this is liters of HCl solution, which is the mixture of HCl and water. And then once I have the moles of pure HCl, I know that that's going to be the same as the moles of sodium hydroxide because I'm doing this reaction stoichiometrically, meaning I'm going to react these in a 1-to-1 stoichiometric ratio. And so this is the calculation for the moles of sodium hydroxide here. We're going to determine the number of moles of sodium hydroxide from how much HCl reacted. Now, the volume of the sodium hydroxide solution we get off the burette. Again, we take V final minus V initial for the sodium hydroxide or the base solution. And we read this in milliliters. And so we need to convert that to liters of sodium hydroxide solution. And this will give us a molarity. And so ideally, the molarity from trial 1, the molarity from trial 2, and the molarity from trial 3 should agree within 0.5%. Now, you didn't have to do the full calculation here. We could just take the ratio. The ratio of acid to base or the ratio of base to acid, that ratio should all agree to within 0.5%. That is, the biggest ratio minus the smallest ratio divided by the smallest ratio times 100% should be less than 0.5%. Likewise, if the ratio holds, then the molarity will hold too. That is, the biggest molarity minus the smallest molarity divided by the smallest molarity times 100%. That would be the percent difference. Should be less than 0.5%. If it's not, then we're going to have M4, etc., however many trials we need to do. And then what we're going to do is we're going to take the average molarity. If you have outliers, you know, we can omit the outlier. But omitting data is very risky because sometimes you have, let's say you have three runs that agree pretty well with each other and a fourth run that's way out. You don't know if the 3 runs that agree with each other are correct or incorrect. Let's say the 3 runs that agree with each other are all wrong and that one outlier was correct. You know, then throwing out that one outlier means that you're getting further away from an accurate answer. And so there are certain tests that we do statistically to throw out data. Otherwise, we don't throw out data. We just kind of average everything. But if you want to throw out an outlier, then there's a test called the Q test. And there has to be a certain number of, you know, what we call standard deviations, like, you know, pretty far from the average, in other words, in order to throw it out. And so normally, well, in this particular experiment, since we're getting it, we choose the best 3 runs. The best 3 runs are going to be the 3 runs that agree. So choose the best 3 and then average those. Or you could average everything. All right, now we've standardized it. And so this is called the standard sodium hydroxide solution. It was unknown before, but now we can call this a standard solution. It's going to be a standard solution because we're going to have at least 4 sig figs. And we went through this process. All right, so that's standardizing or figuring out the composition of the sodium hydroxide solution to a high degree of accuracy and precision, the standardization process. Now, for part 2, we're going to use this standard, the new standard solution that we just made, and we're going to use that to determine the concentration of an unknown vinegar solution. So we're going to determine the concentration of an unknown. Again, it's not really unknown. We know it's about 5% acetic acid of an unknown acetic acid solution. Vinegar. And it depends on who makes the vinegar and what batch it is. You know, the vinegar is going to vary. But the way we're going to determine the concentration is by using the sodium hydroxide standard solution from part 1. What's the formula for acetic acid? C2H3O2. Sometimes I ask for the formula for acetic acid, and some people will write this C2H4O2. Does that look like acetic acid to you? Is it the same formula? Yes and no. Yeah, when I look over here, if I combine these 3 with this one, I get 4 hydrogens, 2 carbons, 2 oxygens. But we have something called isomers. Have you ever heard of an isomer? An isomer is the same composition, but different structure. That would be an isomer. And so we have to be careful with that. And so we don't want to write the formula for acetic acid like this. I don't know where people get it. The correct formula is over here. We could write the formula for acetic acid like this. This is fine as well. What these show is that we have 4 hydrogens. Out of those 4 hydrogens, only 1 hydrogen is acidic. And so this is what we call a monoprotic acid. These 3 other hydrogens are non-acidic because of the structure of this compound. Well, if we only have 1 acidic hydrogen, then that's only going to need 1 sodium hydroxide to neutralize it. And it's going to form sodium acetate, the salt plus water. So what we have is we have an unknown, molarity of acetic acid. Now, acetic acid, there are other ways of writing acetic acid. Another way is HAC, and another way is ACAC for acetic acid. HAC is very common, but since you're learning how to write the formula, we're going to write it all out without using any abbreviations. And so we want the molarity of the acetic acid, just like in the last problem. And so that means we have to figure out how many moles of acetic acid we have for every liter of acetic acid solution. The moles of acetic acid we're going to get from from dimensional analysis and stoichiometry. And so we're going to start off with the volume of sodium hydroxide standard solution. This is going to be in milliliters from the titration. And then we're going to convert this to liters of sodium hydroxide solution. And then we're going to convert this into moles of pure sodium hydroxide. No water. And we could do this in one step if we use the molarity from part 1. So we're going to use the average molarity of sodium hydroxide standard from part 1. And so the average molarity is the moles of sodium hydroxide per liter of sodium hydroxide solution. And so everybody's going to have a different, everybody should have the same, but because of this random errors, it's going to be different. Okay, once we have the moles of sodium hydroxide, then we can just do a direct conversion from moles of sodium hydroxide to moles of acetic acid, because it's a 1-to-1 mole ratio. For every mole of acetic acid, we have 1 mole of sodium hydroxide. And that's where we want to end up. And so it's a 1-to-1 mole ratio. 1 mole of acetic acid, which I'll abbreviate here, HAC, since I don't have much room, for every 1 mole of sodium hydroxide. All right, once I get the moles of acetic acid, then what I'm going to do is just divide this by the liters of acetic acid solution. And so I'm going to start off with the volume of acetic acid solution, HAC solution. This is from the burette in milliliters, and then convert that to liters of acetic acid solution. All right, this is one way of doing it. We want the composition molarity, but you know, if you look at the bottle of vinegar, do they use molarity on the bottle? No. Have you ever seen? No, you've never seen it, because very few people know what molarity is. And so instead of molarity, what they have is they have the percent by mass composition. And so we're going to get the composition in 2 ways. We're going to get it in molarity, and we're going to get it in percent by mass. And so what we have to do is we have to do some dimensional analysis to convert from molarity into percent by mass. I'm not going to write the equation here. Try to figure it out. If you get stuck, I can help you. But yeah, and that's the molarity. All right. I forgot to talk about safety. Should have talked about it before day 1 of this experiment. But sodium hydroxide is drain cleaner. If you get it in your eyes, it'll be extremely painful. If you get it in both eyes, you're not going to be able to see. So hopefully if you don't get it in both eyes, then you can make it to the end of the sink here and use these. This is an eye wash fountain. The cap should be on here, but oftentimes the caps are off like this. So if the caps are off like this, or even if the caps are on here, you'll want to flush it a little bit. Because we don't know if some sodium hydroxide splashed in here. If it's splashed in here, then you don't want to spray your eye. Spray it off. And so go ahead and flush and then go ahead and irrigate your eye. If you get in both eyes, it's going to be hard to see because it's going to be very painful. So if you see somebody cringing with pain, or you want to help them over the eye wash and then help them irrigate their eyes. The eye wash is located on the ends of the bench with the sink. We also have a eye wash over here. It looks like a drinking fountain. You can go to that one as well. We have a safety shower there. There's a pull handle for the safety shower. So if you get chemicals all over, let's say you splash it all over your clothes and your clothes are soaked with drain cleaner, then you want to go over there and just rinse off. Get as much of it off as possible. Now, if you do get drain cleaner in your eyes, how long do you need to flush your eyes out for? 15 minutes. And then you think, why so long? Because, it's just on the surface of your eyes. You rinse it off after a minute, it should be gone, right? It turns out it's not, because your eyes are like a sponge, and they'll absorb the drain cleaner. And so if your eyes absorb the drain cleaner, and then you need to wash the drain cleaner out of the sponge, how long do you have to rinse the surface of the sponge for? A long time. Because you can't squeeze. Unfortunately, you can't squeeze it out. Well, you probably could, but that'd probably crush your eyeballs. But here, if you're trying to wash a dirty sponge, it's going to take a long time. So 15 minutes is torture. I've done it before. 15 minutes like this. And pretty soon it's like, it's hard. It's really hard to sit there for 15 minutes and irrigate your eyes. Especially if they start feeling much better. Initially the pain goes away pretty quick, but you have to be careful because it gets absorbed. Not only you should flush or wash your eyes for 15 minutes, but if you spill some on your arm, how long do you need to wash for? That's the same 15 minutes, surprisingly. And so 15 minutes is a guideline. I don't know if that's actually accurate, but it's easier to remember. It's just easier to remember one number versus two different numbers. All right. Other things, if your clothing catches on fire, which we're not going to use any burner today or flammables, so you don't have to worry about that. But the best is just you can use an eye wash to extinguish your clothing. Or over there, the safety shower. We used to have a fire blanket, but they don't recommend the fire blankets because the water will quench a lot of the heat, which will lessen the amount of burn damage to tissue. Versus a fire blanket doesn't quench the heat, the kinetic energy. Okay. All right, so we'll talk more about safety as we go along, but that's the safety rules for today. All right, any questions? You'll have to bring a beaker for your unknown vinegar solution, and you're going to have to record the unknown number of your vinegar solution into your notebook. So, for example, you should have recorded the the HCl concentration in your notebook. Make sure you have all the data, especially the unknown number, because if you turn in the report without the unknown number, I can't grade it, and I have to give you the maximum deduction for your unknown grade. What you want to do is you want to just try to get the concentration accurately and precisely, and so your grade is going to be partially based on how accurate your experimental results are. Okay. All right, I'm going to stop talking, and then you can go ahead and check out the equipment now.